Hi, I'm Joseph Movsesian. Today is November 28th, 2025, and the function I'm going to be going over today, the rational function, is x minus 1 times x plus 2 times x minus 3, all divided by x minus 3 times x minus 4 times x plus 1. So let's get into this. So we first need to check if this function satisfies all the conditions. So r of x is basically f of x over g of x, and f of x and g of x are polynomials once we simplify everything. So it satisfies that condition. F of x has two roots and so does g of x. R of x has two roots. The vertical asymptote of the function is x equals 4 and x equals -1. There's a horizontal asymptote at y equals 1. There's a hole at x equals 3, and we know that there's a hole because we cancel out the x minus 3's from top and bottom. So when we plug in 3 into our function, we get -2.5, and our hole is 3 comma -2.5. So it satisfies all 6 conditions. This is our graph of the function. So as we can see here, as x approaches -1 from the left side, we can conclude that r of x is equal to -infinity. But if it approaches from the right side, r of x is equal to positive infinity. And the same applies for over here, where at the infinite discontinuity at x equals 4. So from the left side, r of x is equal to -infinity, and from the right side, it's equal to positive infinity. We can see here that at 3 and -2.5, there's a hole. And yeah, I color-coded the functions and all the asymptotes. So then we need to find the first and second derivative. Now, in order to find the first derivative, we have to use the quotient rule. So once we use the quotient rule, we multiply, we combine like terms, all that stuff, and we end up getting the simplest form right here, as you can see below. Now, we do the same thing for the second derivative, but there's a lot more combining like terms, a lot more simplification that we need to do. And yeah, this is our second derivative over here. The graph analysis. So the function goes through the x-axis, which are also known as intercepts, at x equals 1, 0 and -2, 0. These are the points. The critical points, which are basically the points where we set the first derivative equals 0, are x equals -1 and x equals 4. The graph does not increase in any intervals, but it does decrease throughout the whole thing. As you see here, from -infinity to -1, from -1 to 3, from 3 to 4, and from 4 to infinity. Since the graph is decreasing the entire time, that means we can conclude that there is no local extrema. The inflection points are basically when we set the second derivative equals 0, and we get x equals -1, x equals 0.623, and x equals 4. The graph is concave up from -1 to 0.623 and from 4 to infinity. The graph is concave down from -infinity to -1 and from 0.623 to 4. There is a hole at 3, -2.5, which we stated earlier. The mean value theorem states that for a continuous function that is differentiable on an open interval, there exists at least one point where the tangent to the curve is parallel to the secant line connecting the endpoints of the interval. So I chose the interval from 0 to 2, and we can conclude that r of x is continuous and differentiable on the interval. Now, in order to find r prime c, we have to use r of 2 minus r of 0 is divided by 2 minus 0, which is basically our interval point, and we get -7 over 12. We set that equal to our first derivative, and then we cross multiply. We multiply over here, use the distributive property, combine like terms, get everything on one side, set everything to equal to 0, which ends up being 0, and we find that c is equal to 0.623. The extreme value theorem states that if a function is continuous on a closed interval, then it attains both a maximum and a minimum value on that interval. So I chose a different interval for this one. It was -0.5 to 1.5. Our critical points are -1 and 4, as we stated earlier, but these critical points are outside the interval, so all we need to do is use the endpoints. So once we calculate the endpoints, we get that r of negative 0.5 is equal to 1, and r of 1.5 is equal to negative 0.28. So our absolute maximum is negative 0.5 comma 1, and our absolute minimum is 1.5 comma negative 0.28 on this interval. So the tangent and normal line. I chose a point x equals 0, and I plugged it into our function and got 1/2, which is our y value. Then I found I used the derivative function. I plugged in 0 into there, and I got negative 5/8. Our tangent line, if we input all this stuff into the point-slope formula and simplify a little, we get our slope-intercept formula, which is y is equal to negative 5/8 x plus 1/2. And our normal line is just the slope reciprocal, and we left that in point-slope formula. This is the graph here. We can see the tangent line crosses right there, touches it, and the normal line is perpendicular from it. Thank you for watching.